Hi, my name is Krish, and I'm going to be presenting some joint work with Sanjeev Khanna, Ashwin Padaki, and Eric Waingarten. The title is A Polynomial Space Lower Bound for Diameter Estimation in Dynamic Streams. And the setting is the following. I established the metric space M endowed with a distance function d up in the sky. And your task is to come up with a streaming algorithm such that when I present points to you in a streaming-like fashion, at the end of the stream, your algorithm must return the exact diameter of this point set. In particular, in this setting, in this model, we allow the algorithm to make arbitrary distance queries to the metric space M. And in the streaming setting, we care mostly about space efficiency. So the algorithm must have some efficient space representation of the dataset, and at the end of the stream, provide some approximation of the diameter. One simple and trivial way to do this is for the algorithm to just maintain which points it's seen during the stream. Then at the end of the stream, it can just do a brute force computation using its distance queries to the metric space to find the maximum distance between any 2 points. This trivially takes order and space, and a natural question then is this the best we can do? As it turns out, if you want to compute the diameter exactly, there exist hard metric spaces where you require omega n bits of space in order to accomplish this task. So maybe we would try to relax the problem and allow for approximation of diameter. In this case, when we're still thinking about insertion-only streams, is there something better we can do? In particular, I want an approximation algorithm that uses sublinear space. And it turns out the answer is yes. The algorithm is as follows. I will store some and commit to some anchor point at the beginning. And as the stream progresses, I will maintain the radius around this anchor point for the entire stream. This gives us a bounding ball around this central point. And because the radius is a 2 approximation to the diameter of the entire point set, outputting this radius gives us a 2 approximation with log n space. The log n here comes from storing the pointer to our central point that we committed to, and additionally there will be a log delta term where delta here is the true diameter, an additive log delta. Okay, what about dynamic streams? In this setting, I'm allowed to not only insert points, but delete points from my stream. So in this case, here I've inserted x4 and also deleted it at the end of the stream. So in the final point set, x4 is not present. The approximation to the diameter that I want to output is the diameter of the points at x1, x2, and x3. And the natural question is, can we use some ideas from the insertion-only setting to come up with space-efficient dynamic streaming algorithms? And really at the core of the insertion-only algorithm is that we've committed to some anchor point at the beginning and compute the radius around it. So the order here matters because we're only allowed one pass over the entire stream. But in the dynamic streaming setting, no matter which point I commit to, there's always an adversarial stream that will delete it later down the line. And so the real crux of the issue here is that it's unclear how to identify the surviving point a priori. And maybe this should give you some intuition for why the problem is hard in dynamic streams. And so I guess the next natural question is there any setting in which we can say something non-trivial? As it turns out, a very specific setting in L infinity, where all your points lie on the grid with integer-valued coordinate entries from 1 to delta in d dimensions, there's a deterministic and exact dynamic streaming algorithm that uses space order d times delta. How does the algorithm work? It's simple. Because we're in L infinity, all I have to do for each coordinate is independently maintain a histogram for each value. Then, because we're working in L infinity, all I have to do is look at the histogram I've stored for each value, for each coordinate, and compute the maximum gap along that coordinate, then take the maximum over all coordinates. Okay, well, armed with this, can we somehow generalize this result to general metrics? There's this embedding result by Matuszek that says, well, any metric space M can be embedded into L infinity with distortion 2c minus 1 and dimensionality k on the order of n to the 1 over c. And, well, this would immediately imply a dynamic streaming algorithm for c approximate diameter in general metric spaces using order delta times n to the 1 over c space. But perhaps this dependence on delta here is slightly unsatisfying because if delta is some large polynomial in n, this is clearly worse than just the trivial algorithm which is to store all our points and brute force compute the diameter at the end. So a main theorem of our paper is that there exists a dynamic streaming algorithm for C approximate diameter in general metric spaces using n to the order 1 over C space. We're getting rid of this dependence on delta. But what about lower bounds? So now that we have this clean upper bound result for in general metrics, it's natural to ask about lower bounds. Well, there's been a lot of work on these problems, in particular high-dimensional geometric problems in the dynamic streaming setting. So for example, Euclidean MST, Euclidean facility location, EMD, and even Euclidean diameter. All of these problems now have dynamic streaming algorithms that have space like polynomial in n, and in the exponent, something that decays like 1 over poly c. But unfortunately, there aren't many well-known lower bound techniques to prove non-trivial polynomial space lower bounds for any of these. Diameter, being the simplest of these high-dimensional geometric problems, gives us like this holy grail motivating question, which is, can we show a polynomial space lower bound for Euclidean diameter? And the answer, unfortunately, is not yet. But what we can show is the existence of a metric on which diameter is hard, which is a necessary precondition. So informally stating the main result of our paper is that there exists a metric space M, where any dynamic streaming algorithm that C approximates the diameter in this metric requires n to the omega 1 over C space. And so for the remainder of the talk, I'm going to kind of go through some directions that you might naturally try, and ultimately the directions that we chose to use to get the result. When we want to show dynamic streaming lower bounds, a natural approach is to come up with a suitable communication problem and reduce from it. This is a very well-known communication problem known as the indexing, and the setting is that Alice gets some input bit string, n-bit string x, Bob gets an index I, Alice is allowed to send one-way communication to Bob, and then Bob, using this information, must output xi. This is a very well-studied problem in the communication complexity literature, and it's known to have strong lower bounds, in particular that even for randomized protocols, you need omega n bits of space of communication. And so I'm going to consider the indexing a variant of the indexing problem, which I'll call indexing with a twist. And in this setting, Alice gets the same n-bit string, Bob gets an index I, but he also gets some additional knowledge about Alice's bit string x. Here again, Alice gives one-way communication and Bob must output xi. But the structure of this knowledge leads to many different variants of the problem. In particular, one variant is called augmented indexing, where the structure of the knowledge that Bob gets is exactly the prefix x1 through xi minus 1 of Alice's bit string. And again, this is a well-studied problem that's known to have strong lower bounds. Omega n bits of communication are required even for randomized protocols. But the type of knowledge we'll be considering is the following. I draw some bipartite graph with the following promise. In the shortest path metric on this graph, if I look at the pairs of corresponding nodes, ui and vi, their distance is at least 2c. So corresponding nodes are very far apart in this graph. And I'll think of the vertices u corresponding to Alice, the vertices v corresponding to Bob, and I'll think of Alice's input, the n-bit string, encoding a subset of this vertices of u. Bob again gets this index I, as well as the structure of the information he gets is a bit string y that almost looks exactly like Alice's x bit string, except in a few crucial indices. At index I, and at all those indices j that lie inside the neighborhood of vi, Bob receives no information about Alice's bit string, so it's blocked out. And the claim now is that if you had an algorithm to distinguish between diameter 2c being larger than 2c or smaller than 2, this allows us to distinguish whether xi equals 1 or 0. And why is this the case? Well, it's a simple reduction. Alice will insert all those points to uj, for which xj equals 1, into the diameter estimation algorithm and hand the memory contents over to Bob. Then Bob will delete all those vj for which yj equals 1 and return the output of the algorithm. Note that when So the final point set that's encoded in this is exactly the point set containing I and the neighborhood of vi. So if it turned out that xi was 0, the final point set is contained entirely within the neighborhood of vi, which would have small diameter, smaller than 2, because there's a 2-hop distance from any node in the neighborhood to any other node in the neighborhood. But by the promise of this graph, if xi equals 1, the distance between ui and any neighbor of vi is far. And so that completes the reduction. And as I mentioned earlier, this communication game looks a lot like indexing, but with a twist. And in the literature, it happens to be studied under a different name of index coding with side information. Its communication complexity remains open, but progress has been made when we restrict specifically to linear protocols over finite fields. So there's this theorem by J. Ram et al. In 2006 that says specifically for linear protocols over F2, there's this quantity that depends on the knowledge graph G that fully characterizes the number of the communication complexity of this problem. I'll define min rank on the next slide, but for now just know that it's a quantity that depends on the knowledge graph G. If we don't consider it just a static graph, but instead a random graph, a random bipartite graph, it was shown by Nogalan et al. In 2020 that the min rank of this random bipartite graph is at least NP with very high probability. And so what does this give us? Well, combining the reduction from the communication problem to the streaming problem, as well as this lower bound on the on linear protocols from the communication problem, we immediately get a lower bound on linear sketches over F2 for dynamic streaming of diameter estimation. And I'll remark that actually when we generalize this to linear protocols over any finite field, these results will still hold. But because the general communication complexity of this problem has not been fully characterized, we'll need a different approach to show general streaming lower bounds. Here's the definition of the min rank that I promised earlier. I'm going to fix some graph G, let's say it's a bipartite graph, and I'll consider the following incomplete matrix induced by this graph. So it'll have two properties. The first is that there are entirely ones on the diagonal, and the second is that the ijth entry of this matrix will be 0 if the corresponding pair of nodes has an edge between them, between ui and vj. And then the min rank is defined as the minimum rank over all real completions of this matrix M. So if we can't go via this communication complexity route, the ultimate route that direction we went to get this lower bound result is following this other line of work that establishes a surprising connection between streaming algorithms and linear sketches. This is work by Ganguly in 2008 and Woodruff et al. In 2014. And the result is as follows. I choose a decision problem P and fix a distribution D over integer frequency vectors X that lie from 0 to M in n dimensions. Then, given a dynamic streaming algorithm A for this decision problem, I can extract a linear sketch T such that T is correct on P with very high probability over D. And a couple of things to note here are that T is randomized, and I've denoted its dimensionality here as S, where S here will crucially depend on the space of the original dynamic streaming algorithm. The exact dependence will become important later. And so, armed with this new result, maybe we can try to hope for and use this result in the following way to get a lower bound for diameter estimation. In particular, I'll fix a distribution D over frequency vectors. Assuming the existence of a streaming algorithm, I'll extract a linear sketch. And then maybe I can hope to find a matrix or construct a matrix H such that when I left multiply T by H, it will look like a min-rank completion of some random bipartite graph. Well, then we get the following chain of inequalities. S, which is the rank of T, will be at least the rank of HT, which will be at least NP by the result of Alon et al. And this ultimately will give us a lower bound on the rank of T. But there's a big problem. When we're actually constructing our matrix H in the paper in the argument, we really require m to be very much larger than an exponential in S. In the reduction of the Woodruff paper, however, the dimensionality of the sketch that we extract looks something like the space of the original streaming algorithm times log m, where again, m is like a parameter that controls the size of the support of the distribution. So ultimately, this will give us a vacuous lower bound because S, on the previous slide, we saw that S is at least NP, and log m looks like S, so space, the space of the original streaming algorithm, the only lower bound we can recover is a constant bit lower bound. So this log m right here, although it looks innocuous, because our support of the distribution needs to be so large, ultimately is the real culprit in losing the polynomial space lower bound that we want. So a natural question then is this log m necessary? And the answer is yes for general functions, which is the setting under which the Ganguly paper and Woodruff et al. Study this problem. So in particular, to see why, consider the following function. The function on a frequency vector x is x1 mod 2. An optimal streaming algorithm for this problem would just store one bit, indicating the parity of the first entry in our frequency vector. But on the other hand, for any correct linear sketch, it must be the case that t times the first basis vector cannot be 0 with high constant probability. And therefore, t times I times e1, scaling this matrix vector product by all I in m from 1 to m, will result in m exactly unique states, and therefore log m space. So we need some way to get rid of this log m. And in the original result, the actual reduction to go from streaming algorithms to linear sketches has two steps. The first is to a path-independent algorithm, which I won't define here, but the important part is that this reduction is lossless. And the second is going from taking a path-independent algorithm and extracting out a linear sketch, which for general functions, this is where we lose the log m. But in our paper, we identify a class of functions known as scale invariant functions for which we can remove this log m. And by scale invariant functions here, we just mean if you take your frequency vector and scale it up by a positive integer a, this does not change the value of f. And in particular, diameter lies in this class because scaling the frequency vector does not change the support of the point set and therefore does not change the diameter of the point set. And so the results of our paper are this new connection between streaming algorithms and linear sketches for scale invariant functions, in particular ridding the dependence on this log m. The second is then a lower bound on linear sketches for diameter. The combination of the first and the second results in the lower bound for a polynomial space lower bound for general streaming algorithms for diameter estimation. The third, which I touched on earlier, is this tight upper bound for diameter in general metrics, which works by embedding our metric into L infinity, and then instead of doing the histogram idea, we store L0 sketches in every coordinate. That's the high-level intuition. The fourth result, which is just a corollary of the third and the second, and the third and the polynomial space lower bound for general algorithms, is that our hard metrics, the random bipartite graphs, are an easy-to-describe metric that are hard to embed into L infinity. So while this doesn't improve on the dimension distortions trade-offs for L infinity, it gives us an easy-to-describe metric, which is hard. And so, in conclusion, what I've shown is that in our paper, we show a polynomial space lower bound for diameter estimation. We show the existence of a hard metric. But really, what we would like is for this to be, what we would like to show is that in Euclidean space, diameter estimation is hard in dynamic streams. So, and secondly, we would also like to ask, this lossless reduction from linear sketches to streaming algorithms for scale invariant functions is very general and of general interest. Is there somewhere else that we can apply this?